On November 7th, 1940, a newspaper editor named Leonard Coatsworth was driving across a brand new bridge in Washington state when the road beneath his car began to heave. Within minutes, he was crawling on his hands and knees towards solid ground, leaving his car and his daughter's dog behind. 40 minutes later, the bridge he had just escaped tore itself apart and dropped into Puget Sound. It had been open to traffic for exactly 4 months and 7 days. What happened on that bridge would go on to change how every suspension bridge in the world is designed. For decades, Tacoma and the Kitsap Peninsula had sat on opposite sides of Puget Sound. Separated by a narrow, wind-funneling channel, the region wanted closed. Funding finally came through when the U.S. military backed the project as a strategic link to the Bremerton Navy Yard. Construction began in November 1938, and the bridge opened to the public on July 1st, 1940. About 10,000 people turned out for the dedication. At 2,800 feet, its main span was the third longest suspension bridge in the world, behind only the Golden Gate and George Washington bridges. It had cost roughly $6.4 million to build.
Leon Moiseff designed the bridge, a respected engineer who had also worked on the Golden Gate Bridge. He wanted the Tacoma span to be sleek, the most flexible suspension bridge ever built. Rather than open steel trusses, which let wind pass through a bridge deck, he chose solid plate girders beneath the roadway. At the time, this was considered elegant, modern, and, according to the engineering standards of the day, safe. Frederick Burt Farquharson, an engineering professor at the University of Washington, had been watching the bridge closely since it opened. He wasn't convinced its motion was harmless.
That motion had started before the bridge even opened. During construction, workers noticed the deck rippling in wind that should have caused no reaction at all. Some crew members reportedly sucked on lemons to fight seasickness. The bridge earned a nickname almost immediately: Galloping Gertie. Rather than alarming the public, the movement became an attraction. Drivers would wait for a windy day, then cross the bridge specifically to feel it sway beneath them. On the morning of November 7th, winds in the Narrows reached roughly 40 miles per hour. Not an unusual storm, and well within what engineers believed the bridge could handle. But this time, the motion didn't stay as a gentle up and down ripple. It shifted into a violent twisting motion, the two sides of the roadway rising and falling in opposite directions. Farquharson arrived to observe it directly. Coatsworth, driving across with his daughter's Cocker Spaniel, Tubby, in the back seat, found the road tilting so sharply he could no longer control the car. He abandoned it mid-span and crawled to shore. Farquharson tried to reach the dog and pull it from the car, but the frightened animal wouldn't leave, and the professor was forced back. At 11:02 a.m., a 600-foot section of the center span broke free and fell into the water below. Within another 8 minutes, most of the rest of the span followed it down. The collapse was captured on film by Farquharson himself and by Barney Elliott and Harbine Monroe of a local camera shop who happened to be filming that day.
That footage still exists, and it remains one of the most studied pieces of engineering film in history. The only fatality was the dog. No people died. In the aftermath, the federal government convened an investigative board that included engineer Othmar Ammann, aeronautical scientist Theodore von Karman, and engineer Glenn Woodruff. Their 1941 report concluded that the failure was not caused by any flaw in the steel, the concrete, or the construction itself. What they found was aerodynamic, not structural. The solid plate girders that made the bridge look so sleek had blocked wind from passing through the deck. Instead, air piled up above and below the roadway and began shedding vortices in a repeating pattern, a phenomenon that fed energy into the bridge's twisting motion. Instead of damping it out, engineers call this aeroelastic flutter. Decades later, many textbooks simplified this into a more familiar concept: resonance, comparing it to a singer shattering a wine glass. That explanation is easier to picture, but it isn't precise. The federal investigation identified flutter,
not simple resonance as the specific mechanism, and that distinction still shapes how the collapse is taught today. Much of the wreckage was never recovered. Portions of the collapsed spans still rest on the floor of Puget Sound, where they've become one of the largest artificial reefs made by human construction. The site was later added to the National Register of Historic Places, in part to protect it from salvage. World War II delayed any rebuilding effort, and a new Tacoma Narrows Bridge, engineered with the lessons of 1940 in mind, didn't open until nearly a decade later. Bridges would never be designed the same way again. Wind tunnel testing, once rare, became standard practice for suspension bridge design. Today, any bridge built with federal funding in the United States must have its design tested against three-dimensional wind models before construction begins. Engineers who once believed thinner and lighter meant more advanced were forced to reckon with a blind spot in their own field, one that a $6.4 million bridge exposed in under an hour. Galloping Gertie stood for exactly 4 months. Its wreckage has now rested in Puget Sound for over 80 years, longer than the bridge itself ever carried traffic. What survived it wasn't the structure, but the film of its final morning. Footage still shown in engineering classrooms to this day, teaching students to look for the forces a blueprint alone can't always predict.